morning, students. I am NV Krishna Rao, Assistant Professor CSC Department. I am handling the compiler design for the 5th semester. Right? So, now we'll discuss leftmost derivation and rightmost derivation. In the last class, we have discussed the parsers, then context-free grammars, and examples for the derivation and derivation trees. Right? So, here now we'll discuss leftmost derivation and rightmost derivation. Right? So here a derivation is basically a sequence of production rules in order to get the input stream. Right? So what is a derivation? Derivation is a sequence of production rules in order to get our input stream. So during the parsing, we take two decisions for some sentimental form of input, deciding the non-terminals which to be replaced, deciding the production rule by which the non-terminals will be replaced. Right? Here, what is the role of the parser? To group the sequence of the tokens into the parse trees. Right? That can be done by selecting the production rules and selecting the deriving the non-terminals of which matches to our given sequence of the tokens, which has followed the syntax rules of the programming language. So here, which decide non-terminal to be replaced with a production rule. So we can have two options, right? Leftmost derivation, rightmost derivation. So we have two types of the derivations. Leftmost derivation, rightmost derivation. Right? Here in the leftmost derivation, we use the leftmost non-terminal to expand. Right? So in the leftmost derivation, we chooses the leftmost non-terminal for the expand to derive a sequence of the terminals. Rightmost derivation. The rightmost derivation, it chooses the rightmost non-terminal, right? It chooses the right end non-terminal to the expand. Left end non-terminal or right end non-terminal. If we always replace left end non-terminals, then we say leftmost derivation. If we always replace right end non-terminals, then we refer as rightmost derivation. Here, a derivation is basically a sequence of production rules in order to get the input stream. Now, the production rules are given as x equal to x plus x equal to x into x gives a. These are the production rules, right? These we represent as production rules. Here, a plus a into a is our input string. The string to be derived, right? If we always replace the left end variable, if we choose the first text from the left side, then the derivation is leftmost derivation. If we use always right end variable, if we always chooses the right end variable, then we refer as right linear or rightmost derivation. Right linear derivation or rightmost derivation. So here x into x, both have the 2x are there. But which x we are replacing? Here in this derivation, if we always replace the left end variable, left linear grammar, leftmost derivation. If we always replace right end variable, rightmost variable, then we refer as rightmost derivation or right linear derivation. Right? So here, if we leftmost derivation means we always leftmost non-terminal to expand. If we choose as rightmost non-terminal in the expand, we refer as rightmost derivation. Here, these are the production rules. E gives E plus E gives E into E gives ID. So, these are the 1, this is a 2 and this is a 3. We have 3 production rules, right? Our input string is ID plus ID into ID. We have to derive ID plus ID into ID. We'll see. Leftmost derivation, right? Here, E into E is there. What is the leftmost? This is the leftmost. We are replacing the leftmost variable. We are replacing the leftmost variable. Then, which production? We are using the production number 1. By using the production number 1, we are replacing E with the E plus E. Then, what is the left end variable? This is the left end variable. So, the left end variable simply E gives ID. E gives ID, right? ID plus E, right? So, here this ID, this will be the next left end variable. This left end variable here, previously we have second, the third production. Now once again we will take the third production, which results to E gives ID, right? E gives ID, right? ID plus E into E. So that E gives as ID. Then ID into I, right? So once again we use the third production from equal to ID, right? E gives ID plus ID into ID, right? So here this is a left hand variable. Here it is a left hand variable. Here it is a left hand variable. The finally this will be the left hand variable. In the derivation of this derivation step, the left hand variable, leftmost variable, we are replacing, right? So this we refer as leftmost derivation, right? Then rightmost derivation. Here in this rightmost derivation, this is a right hand variable, right? So we are selecting the production number 1. Then we are using the production number 2 for this expansion. E equal to E into E, right? Right? Then what is the right hand variable? This is the right hand variable. This is the right hand variable. So we use the right hand variable for the expansion, right? So we use a third step. We use a third step for the expansion. E gives as ID. E gives as ID, right? We use equal to ID. Then once again, what is the right hand variable? This one will be the right hand variable, and we use the third production to replace that E variable with the ID, right? Once again, what is the right hand variable? This is the right hand variable. Then we use the production number 3 to replace E with ID. We'll replace E with ID, right? So here we are replacing in each derivative steps only the right hand variable. Then it is called as the right linear derivation or rightmost derivation. So in deriving the input string ID plus ID into ID, if we always replace left hand variable, then leftmost derivation. If we always replace right hand variable, rightmost variables, then we refer as rightmost derivation, right? Here, representing this in the graphical representation called the derivation tree or Parse tree, right? So here always the root is a start symbol. The start symbol will be the root of the Parse tree, right? And integer nodes represent the non-terminals. The interior nodes will represent the non-terminals in N. The leaf nodes always the terminal are epsilon. The leaf nodes always will have the terminal or epsilon. A node can have the children x1 to xn if there is a production rule A gives x1 to xn. Right? If the production rule A gives x1 to xn, then the node A can have children x1 to xn. Right? So here E gives E into E. So E will be the node, then it giving E into E. Right? Then this is the we are considering the first step. Then the left linear derivation we are using in this one, we are replacing the leftmost variable with its respect to production. Right? Now the E giving as E plus E. Then we are using the left hand variable in this is a left hand variable. By using the production, we are replacing E with ID. Right? E with ID. Right? We are replacing E with ID. So we are representing the derivation of the input string in the Parse tree structure. Right? Then ID equal to ID plus ID into E. So here in this one, this is a left hand variable. So the left hand variable is replacing with a terminal. Right? Then in this one, what is the left? This is a final left hand variable. The left hand variable is replaced with a terminal ID. So giving the final the given input string. So ID plus ID into ID. So we are deriving the input string by using the leftmost derivation. Right? So same thing. In a Parse tree, all the leaf nodes are terminals. All interior nodes are the non-terminals. In-order traverse gives the versional input string. Means grouping from left to right. Grouping the left to right, they will gives the yield of the tree. The leaves of the Parse tree, when read from left to right, are called the frontier or the yield of the tree. Right? A Parse tree depicts associatory and precedence of the operators. The deepest subtree is traversed first. Therefore, the operator in the subtree gets precedence over the operator which is in the parent node. Right? So here one more example. Right? This is a leftmost derivation. So x plus x, x into x, exclusive. Right? This is the input string that we want. So first leftmost is replaced with, then leftmost variable replacing with a, then leftmost variable x replacing with the a, then leftmost variable replacing with a. Right? Then rightmost derivation. Right hand variable. This is a right hand variable. Then this is a right hand variable. Then this will be the right hand variable. We are always replacing with the right hand variable. Then we refer as rightmost derivation. Right? A sentential form occurs in the leftmost derivation and a right sentential form occurs in the rightmost derivation. Right? A left sentential form occurs in the leftmost derivation and a right sentential form occurs in the rightmost derivation. Right? Here we are showing the each one in leftmost derivation and rightmost derivation. So this is a first step. Then this is a left hand variable. So we are expanding the left hand variable. Right? Then this is a left hand variable. Now we are expanding this one now, right? The left hand variable we are expanding. Then in this one, this is the left hand variable. So we are expanding excuse A. Then this one is a left hand variable. Then finally we are expanding the excuse A. So this is a derivation, leftmost derivation, right? We always replacing the left hand variables. Then we can refer as leftmost derivation and left linear derivation. Then rightmost derivation. What is the rightmost derivation? Always replace the right hand variables. In the first we select x equal to x plus x into x, and in this one this is a right hand variable. So we expand x gives a, the right hand variable. Now in this one this will be the right hand variable, and we expand the right hand variable. We are expanding the right hand variable. Now in this one this is a right hand variable, so we are expanding this right hand variable as excuse a. So this is the right hand variable, so we are expanding the right hand variable excuse a. So in the finally this is the right hand variable that is left over, so finally we are expanding this one. So here these are the different derivative steps for in the rightmost derivation for deriving the input string x plus a into a. Next comes to the ambiguity in the counter-split grammars. Whenever we want to use some grammar protections in the parsers, it should be an ambiguous. If there is an ambiguity means if there are more than one leftmost derivation, or if more than one rightmost derivations, then we say the grammar is counter-split grammars, because the parser has to construct the parse trees from the sequence of the token. But if there are multiple derivation trees, multiple possibilities of construction of the trees, then it is unable to find out the edges in the sequence of the tokens. So it is unable to construct the correct parse trees. So if any grammar is ambiguity, then we must eliminate the ambiguity in the grammar. Right? So a grammar is said to be ambiguous if it permits a terminal string, right? It permits a terminal string to have more than one parse string. That is more than one leftmost derivation or more than one rightmost derivation for the same string. For the same string, it has more than one leftmost derivations or more than one rightmost derivation. Then we say it is ambiguity. The grammar is said to be ambiguous. So if the grammar is not ambiguous, then it is called an ambiguous grammar. To apply the parse trees, the grammar must be unambiguous. Right? Now we'll check this grammar is ambiguity or not. Here a given example is there. Now we'll check. There existing more than one derivation trees, leftmost derivation trees or rightmost derivation trees, then we say the grammar is ambiguous. We'll check by considering. Right? Here S gives production number 1 we are applying. By applying the production number 1, S gives ASP. Then applying the once again production number 1 is giving ASP. Right? Applying the production number 3, we are getting the our required string AABB. We are obtaining the AAB by following the sequence of order 1, 1, 3. But if you observe this one, this also a left linear derivation only. First, we are considering the step 2 as using two S's. Then, we are considering the third step as gives epsilon. Then, we are considering the first step as gives ASB. Then, we are considering the once again first step as gives ASB. Then, finally, we are considering the third step. So here it also a left linear grammar by following the derivative steps 2, 3, 1, 1, 3, right? Which means there are more than one leftmost derivation. So the grammar is ambiguous, right? For any given string, there must be only one derivation tree. If it has more than one leftmost derivation, then we can say the grammar is ambiguous. Now we'll see one more. This is one more example it is given. Now we have to show that it is ambiguous or not. So if it has the more than one rightmost derivation or more than one leftmost derivation, then we say the grammar is ambiguous. So the string we want to derive id plus id into id, right? The string we want to derive is id plus id into id. Then this is the one. So first step we are applying the production number 1. Then we are applying the production number 3, right? This is the production number 3. Then we are applying the production number 2, right? This is the production number 2. Then we are applying the production number 3. Then we are applying the production number 3. Then we are applying the once again production number 3. So this is a derivative steps one by one. Now, okay. Here one more. First, we are applying the production number 2. This is the production number 2. Then we are applying the production number 1. So this is the production number 1. Then applying the production number 3. Applying the production number EUSID. Then applying the leftmost. This is the leftmost. Applying the once again production number 3. Then leftmost. This will be the leftmost. Applying the once again production number 3. So we are getting the id plus id into id. Same input string we are obtaining. But the sequence of steps are different in this both left linear derivation. In both leftmost derivation. Because it has more than one leftmost derivation, so we can say the grammar is ambiguous. Right? The grammar must be unambiguous to construct the parse. Since it has two leftmost derivations possible, ambiguous grammar. Right? Here, it do not guarantee unique parsing and translation. Ambiguous grammar should be avoided. Otherwise, it cannot guarantee unique parsing and translation. Expression evaluation is not clearly defined in the above grammar. Right? If the grammar has ambiguity, then it is not good for compiler construction. So we can't use the productions in the compiler construction. It won't generate the correct parse trace. So no method can automatically detect and remove the ambiguity, but it can be removed by rewriting the whole grammar without ambiguity. Right? So here, if we have the ambiguity, it is unable to generate the correct parse trees. It will generate the different parse trees for different times. So we cannot construct a good compiler. That's why we want to eliminate the ambiguity in the grammar. So here there is no, we can rewrite the complete grammar to eliminate the ambiguity. This is one more example for the if-else statements. Here the grammar is given if expression then statement, or if expression then statement else statement. Now we consider here if E1 then if E2 then S1 else 2. Now we have to map the if statements and else statements. Now we'll check they are mapped or not. Here statement if E1 statement, right? This one has if E2 S1 else S2, right? Here this has one part. If E1 then the second part. Here this S2 is matching, the else is matching to this one. This else is matched with this F. Okay. This else statement is mapped with if. If here this else is mapped with this one. Here in the first parse tree, the else is mapped with the interior if statement. That second if statement is connected with the else. But if you observe in the second parse tree, the else statement is mapped with the outer if statement, the first if statement, right? So here it is resulting to the ambiguity, right? This is a simply if-else statements only, but the grammar is resulting in the ambiguity, right? So here the question is, there are two if statements, if E1 then if E2, then S1 else S2. There are two if statements, one else statement. The else statement should be mapped with, should be combined with the if statement. But which if statement should be combined? Second if statement or with the first if statement? That is the ambiguity in this context-free grammar. So practice this problems and show that these are ambiguous problems or not. We'll discuss eliminating the ambiguity in the next class. For today, I am closing this section. So we discussed the what is the left derivation, the rightmost derivation, and what is the ambiguity in the grammars. So we continue the remaining topic in the next class. Okay, I am closing this section. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.